Hello again. Happy Monday evening. Welcome to the second of our review question answer sessions for the Chem 100 exam. If you have any particular questions or things that you want me to talk about tonight, please leave them in the chat, and I'll try to get to all the questions in the time that we have. I have the objectives from Blackboard here. So I don't know if you can see that. Probably not. That's kind of what we're going to go by. Hey, Alyssa. So if you want me to talk about a specific objective, that's fine. It's even more useful if you have like a really specific question, like why does this do this, or why is this the answer to this question, those kinds of things. But whatever everybody wants to talk about is great. All right, so first request from Daisy. Hey Daisy, for enantiomers versus identical molecules, we'll definitely talk about that. Give everybody else a couple minutes to join up. Hi, Julia. Yeah. So you wanted to take it, and it said handheld calculator not allowed. Yeah, that's wrong. I mean, it should be allowed. I believe I had that set up to be allowed. What you can do. So just to think about how honor lock works. There's no automatic penalties for the honor lock stuff. So like what happens is if it says no handheld calculator and you're using a calculator, the software will like raise this flag that says this person used a calculator. And so we don't care really about that. The things we're going to be looking for, same thing with like, I know some of you are living in fairly close quarters with other people, and there's always like other noise and things like that. Again, not an issue for us. The concerns we have are just like straight ahead cheating. Are you looking stuff up on the internet? Do you have a sheet of stuff that you shouldn't have? That's really all we care about. It's not like you automatically lose points for violating one of the honor lock rules. So I'm going to check it right now while we're here together, because I believe I can just change that right now if it's wrong. So yes, you're correct. That is not. Let me check everything else here. Okay, so thank you for letting me know. I must have hit the wrong button. So that should be fixed now, and it should not say anything about calculators not being allowed. For this one, it shouldn't pause your exam. It should just flag it as saying like this thing happened. If you're having other trouble with it, certainly let me know. I know there's some different types of proctoring things out there and some different settings you can put on there. I don't have a lot of experience with the tool, so I could definitely mess it up, or I could definitely have caused some problems. But just let me know. I know we've had a few people take it successfully already, so things seem to mostly be looking okay. For anybody, if that kind of thing comes up when you're doing it, please email me. and Professor Lemkow, we are both like on our email constantly for the next couple of days because we want to make sure to answer all the questions that come in from the exam. So we'll be able to get back to you right away if you have any issues. But thanks for coming tonight and letting us know. All right, let's get into some chemistry then. So we've got requests for enantiomers, monosaccharides, and stereochemistry. That's going to kind of go together. Formulas, DNL, and anything else that you want to go over. Oh, hi, Maria. Just leave it in the chat, and I'll keep coming back and try to get through everything. So this is where we left off last time. Let's get into enantiomers, what that means. Now, when we talked about this in class, we looked at a couple different things, and we looked at stuff like a carbon atom with 4 different things connected to it. And then we said, okay, if you take the mirror image of this, it's actually not the same. And if you go back into that video, you can see where we drew it and manipulated it around. So the way the place that this comes up most significantly for us, certainly there is this, but then in the monosaccharides. So when we look at a structure like this, we recognize that because there's sort of a different thing on each of these carbons, these 4 carbons in the monosaccharide are all stereocenters or centers of stereochemistry. So the order or the orientation, the 3-dimensional orientation of where everything is as connected to those carbons is important. So this would be a D sugar, like D glucose. Actually, yeah. And then if we flip all of these OHs to the other side, then we'd have the L. So we'd have the enantiomer. So enantiomers, the way that we defined it is the enantiomers are non-superimposable mirror images. So if you take the mirror image and it's not the same, then those are enantiomers. So identical and stereoisomer is not the same. Identical means identical. It's the same molecule in all respects. Stereoisomer means it's not the same molecule, but it only differs by this 3-dimensional orientation. So the way everything's connected to each other is the same. Like this, the C is connected to this C, and this C is connected to this C. Those are the same, but the orientation in space is different. So one molecule has the OH on this side, and the other molecule has the OH on the other side. That's what makes stereoisomers different. So the biggest place that we've seen these in this class is looking at D versus L for sugars, or R versus L, D versus, excuse me, or those for amino acids. Most naturally occurring sugars are D. Most naturally occurring amino acids are L. But I don't think you need to know that. All right, so let's take a look now at while we're talking about this, how do we know D versus L? Well, if the structure is drawn in this way, you look at that bottom carbon, that bottom stereo center, and if the OH is over on the right, it's D. If the OH is over on the left, it's L. So that always works, assuming everything is in this orientation, which in this class it should be. If it were in some other orientation, you'd have to twist it around to get it in the right spot. Okay. So a question from Michael in another section, an overview of what you will be testing on in your somewhere in your Blackboard shell, or if you don't have it from your instructor, you can email me and I'll get it to you. But I'm pretty sure he's got it. There should be a list of objectives. So each section, each week, each topic had a list of like anywhere from 4 to 8 or so bullet points. Those are the objectives that will be on the final. All right. So naming monosaccharides. And I guess when you say stereochemically identify them, that's the D versus L thing. Naming them, that's not something that is on the that's going to be on the exam. In a biochem class or organic chem class, you might need to memorize some of the structures. So like this is glucose, this is galactose, this is maltose, whatever. Um, and that will you'll have to memorize those. But there's no like it's not like with the ionic compounds where there's a particular way of naming it, and if you just sort of know the rules, you can figure out what the name is. That doesn't work with these. You just have to memorize it, and that's not an objective for the class. All right, so while we're talking about stereochemistry, I'm going to grab this question from Jennifer. What is a diastereomer? So a diastereomer is any other kind of stereoisomers. Stereo, man, it's hard to write and talk at the same time. Isomers. So not enantiomers. So for example, if we go back to this sugar structure here, if we take the mirror image of this, so we flip all the OHs, we have the L version of that sugar, which is its enantiomer. If we only flip one OH or two OHs or three OHs, then we've formed a diastereomer. It's a different structure. It's a different stereoisomer, but they're not enantiomers. They're not exact mirror images. Another way that that comes up is when you don't have chirality at all. So like trans versus cis alkenes, those are diastereomers. They're not mirror images, they're not chiral, but they are still a type of stereoisomer because even though everything's connected in the same way, there's a different three-dimensional orientation. So those would be diastereomers. So any other kind of structures that are stereochemically distinct but are not necessarily or that are not enantiomers are going to be diastereomers. Yeah, all of these will have the same atomic mass, all of these will have the same formula, and any of these would have the same connectivity. So the atoms connected in the right order, in the same order, like C, 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 O, C, whatever. They only differ by how they're connected in 3 dimensions. So I don't know what you mean by etc. I assume, but yeah, that's what we're talking about. The reason those are important different categories, by the way, is because enantiomers are exact mirror images, they tend to have the same physical properties and mostly same chemical properties as well. So they have like enantiomers will have identical melting points. They'll have the same polarity. They'll have the same boiling points, all that stuff. But diastereomers might not, because the polarity might be different because some of the OHs are over here, some of the OHs are over here. So it's usually easier to separate diastereomers, but it's very, very difficult chemically to separate mixtures of enantiomers from each other. All right, so next we've got, I don't want to miss anybody. What formulas should we know? So you mean mathematical formulas, I assume there? So you should know how to convert units in general. You don't have to know all of the various conversion factors, like you don't like between the English and metric systems. You only need to know the specific numbers that are in the objective. So you need to know like kilo, centi, and milli, and deci, and I don't remember the ones that are specifically listed in the objectives. You need to know that there's 760 torr in an atmosphere of pressure. I think that's about it for the conversion factors. Other formulas you need to know, You should know how to convert temperature. Temperatures, Fahrenheit, Celsius, and Kelvin. In terms of other mathematical formulas, I think that's probably it. I'm going to take one more look at the objectives here. I mean, moles, like, okay, so a couple more. So if I'm looking at the objectives, week 8, calculate the number of moles in a given mass, calculate the number of grams in a given number of moles, calculate density. Those would all be formulas that you need to know. And then going into 10, solutions and mixtures, you would need to know how to calculate molarity and percent mass. Yeah, molarity and mass percent calculations. I think that's it. There wasn't much math after that. In terms of chemical formulas, you should know the polyatomic ions, certainly. Make sure that you know those, the ones that are listed, and then the acids and bases that are listed. I think we talked about that yesterday. Sulfuric acid, hydrochloric acid, nitric acid, sodium hydroxide, potassium hydroxide. Those would be the chemical formulas you should know. All right, so then I think next is reactions of amino acids. All right, so let's take a look at some random amino acids that happen to be on my mind for some reason. We've got, let's say this one. This is alanine with its CH2 there. And then what was the one we were looking at last time? Threonine here, right? Right here. Tyrosine, sorry, tyrosine. I always get those mixed up. All right. So 2 amino acids here. And you can see that as we talked about last time, amino acids tend to have the same type of, well, they all have the same structure in that they have this alpha carbon in the middle. They have an amine on one side and a carboxylic acid on the other side. Based on the pH of the system, sometimes those are shown as an ammonium, so H3N+, and sometimes these are shown as a carboxylate, CO2-, but same idea. And then you have this thing coming off of it that we call the side chain, and all the amino acids are distinguished by their side chains. So when they react, when they connect to form the primary structure of the protein, the sequence of amino acids, those are going to be reactions where we take one of the, we kind of like combine this stuff. So let me draw this out so we can see it better. I'm just drawing out all the atoms there. And we're going to take 2 hydrogens and an oxygen and make that water. And then connect what's left. So the carbon here is going to connect to this nitrogen. Everything else is going to stay the same. So however the structures are drawn, we now have, I'll move this up so you can see. We now have something like this. And if we're keeping the angles, by the way, they end up, the next side chain ends up flipping up. It's not really important. You can kind of just draw it straight if you want to. I think they're usually drawn more just like in a straight line. But because I was using line structures and zigzags, I just kept it that way. But this is now our dipeptide. So 2 amino acids linked together. And the order that the amino acids are linked together is important, because if we flip these, if we reacted with the carboxylate of tyrosine, right? Second guessing myself. I think it's tyrosine. And we so we'll say this one. If we reacted with the carboxylate of this one and the amine of this other one, then we'd have a different peptide, a different dipeptide in the opposite order. So you have the carboxylate from one reacting with the amine of the other, and you have something like this. And then this functional group that they have created right here by joining together can be described either as an amide, which is kind of the generic type of functional group that it is, having a C double bond O carbonyl and then a nitrogen coming off of it. That's an amide. But it's also described as a peptide because that's specific to proteins. So when amino acids join, you form a peptide bond. When other types of molecules join, you could make that same kind of functional group, but it would be called an amide rather than a peptide. So peptide describes both the bond and the whole thing that you make. So you can have a dipeptide, a tripeptide. Bigger than that, you might call it an oligopeptide or a polypeptide as you get more and more things. And then as this gets bigger and bigger and bigger with more amino acids, that's what forms the primary structure of the protein. So all these amino acids join together in a particular order. That's our primary structure. All right, so looks like next, and the last request so far, unless if I missed your thing, just put it back in again. I didn't mean to skip you. I'm just trying to see. But it looks like Daisy had another request. Describe and give examples of the different functions of proteins in the body. All right, so this is one that you may want to look up. You're not going to have to know like specific ones here, but if you look in the book, in the protein chapter, you can see some examples there. I think it's that very first section, properties of proteins. So let me pull this up on the screen here. Yes, you can kind of see this behind me. Put over a little bit. Okay, so we've got the digestive enzymes. You've got transport proteins. You've got structural proteins, hormones, defense proteins, contractile proteins, storage proteins, and so I think there's probably another category of enzymes than just the digestive ones. The digestive proteins are probably the most important because that's how you're going, or not the most important, but those are important because they break down your food and they are stable in that low pH of your stomach. So do you need to know everything on this table? No. I think you need to know, you need to think about what the protein is doing and be able to categorize it accordingly. So, do you know that you don't have to know that, for example, amylase, which breaks apart amylose, which is a starch, you don't necessarily have to know that that is a digestive enzyme, but if it says that amylase breaks down starch into monosaccharides, what category would that be in? And it would list some categories, and enzymes would be the category that you'd put that in. So that's a catalytic enzyme protein, as opposed to like if it said, oh well, actin proteins in the muscles cause the muscles to, pull the arm up or something like that, then you'd categorize that as a contractile protein. So I would maybe know the categories that are listed in the objective. So which Daisy copied over here in the chat: structural, contractile, transport, storage, hormone, enzyme, and protection or defense. And then just think about like what are the things in the body, what what are those categories doing in the body? Um, you don't need to know specific names of proteins, but you should know the categories and what they do. So, and I think some of these you probably already know just from prior learning, but the ones that you don't, I would know those words and their definitions. You don't need to know specific proteins. All right. So then Daisy asks about nucleic acid structure. So for nucleic acid structure, let's get into that chapter here while we're here. All right. So a couple important things about that. Let's get to the structural picture down here. Okay. So we have the like double helix type structure of DNA that everybody knows. We zoom in on that and we look at the different sections. So we have the two backbones, that's what these things are called, the stripy or the blue twisty parts. Those are the backbones, and the backbones are made of alternating phosphodiesters and sugars. In DNA's case, it's deoxyribose. So deoxyribose is bound to the phosphate. Then you got another deoxyribose, then another phosphate, another deoxyribose, another phosphate, and that forms the backbone. The other backbone is formed the same way, but just in the opposite orientation. So it's sort of like upside down. So one, you can think about it going this way, one going this way. They use these numbers 5 and 3 because if you count around the ring on the deoxyribose, 1, 2, 3 is this carbon, and then 4, 5 is this carbon. So this side, the 5 is on the top, we would say, going to the 3, and then this way it's just flipped. So it's just the opposite direction. And those are all covalent bonds. So phosphodiester functionality bonds. Then each deoxyribose sugar is connected to one of these bases, one of these nitrogenous or nitrogen bases that are these big molecules that look like this. And then there's actually a different one called uracil in RNA instead of thymine. But then those nitrogen bases hydrogen bond to hold the two strands together. So when we look at, let's make it a little bigger. When we look at how these base pairs hold each other together in the double helix, we're talking about hydrogen bonding. And if we want to be more specific with that, I think there's another picture right here. Too big. So for example, between adenine and thymine, you have the hydrogens from the amine over here, hydrogen bonding with the carbonyl oxygen, the amide oxygen here, and then the hydrogen from the amide there, hydrogen bonding to the nitrogen. And then between the other two, guanine and cytosine, you have the same kind of idea, just it's a different base, so they're different structures. You don't need to memorize the structures of any of that stuff. You just kind of need to know in general, how are they connected? How do we describe that structure? How do we describe that phosphate sugar backbone, and then the nitrogen bases, and then those nitrogens, and then the two sides are held together by the hydrogen bonding between the bases. So to answer Michael's question, then, where do the hydrogen bonds come into play to hold those strands together? So these dotted lines are those hydrogen bonds. And that's kind of that's how one way that DNA functions the way that it does is the covalent bonds in the backbones are a bit stronger. So these hydrogen bonds under certain conditions can break, and it can kind of unzip to then do its transcription or whatever it's going to do. And then those hydrogen bonds can line back up again. So the hydrogen bonds work to hold the strands together. All right, so then another question about DNA. Yeah, it is cool. Identify the location of the phosphodiester bond in the hydrolysis reaction of two nucleic acids. I don't think we talked about that one actually. I don't remember really talking about hydrolysis of nucleic acids. If we were to hydrolyze them, then we're talking about these bonds here. So when we hydrolyze, we talked yesterday in the session about hydrolysis in general. Hydrolysis means you're adding water and then you're breaking things apart. And the OH is going on one side and the H is going the other side. So if we just kind of look at this and think of it not as some new phosphodiester thing, but just think of it as like our normal esters, then what's going to happen is between this P, O, and C, this bond right here between the O and the C is going to break. And we're going to end up with, or I guess it's more correct to say that the bond between the P and the O breaks. And then we end up with that OH kind of returning to where it would be in the sugar, and then another OH here. So maybe it makes more sense to draw that. So if we have our different color here. So if we have our phosphodiester like this, and I'm just going to, let's say that's our sugar. This is going down to the other sugar, the 5 sugar. And then we have the rest of the phosphate here. Like that. So if we imagine cleaving one of these bonds, what's going to happen is we're going to get rid of that bond. This is going to become a regular OH, and then there's going to be another OH there. So that's hydrolysis. That's what hydrolysis looks like there. No, hydrogen bonds are not stronger than covalent bonds. Hydrogen bonds are poorly named. Maybe that's too mean. They're inconveniently and confusingly named because they're not bonds really at all. They're intermolecular forces. They're attractions between molecules, and they're weaker than covalent bonds. Some ionic bonds can be stronger than covalent bonds, but hydrogen bonds are more similar to things like dipole forces and dispersion forces. They're in with the intermolecular forces, not the covalent bonds. All right. I think I got everybody's questions so far. What else you got? Sure, yeah. Saturated, unsaturated, and trans fats. All right. So these terms are, in this case, applied to fats, but they're actually general alkane type terms. If we have any kind of carbon hydrogen containing molecule, hydrocarbon like this, it is saturated if it has the most possible hydrogens it can have. So for this molecule, let's see, 2, 4, 6, 8. I drew 10, so this is C10. And in this case, it's going to be H22. So there is no way to have 10 carbons and have more than 22 hydrogens. But there are ways to have fewer than 22 hydrogens. So if we add a double bond here, we now have one fewer hydrogen on each of those carbons. So now we have C10H20. And now we have a compound that we would call unsaturated. So it's no longer saturated because it doesn't have as many hydrogens as it could possibly have. So how this works in fats, specifically in the fatty acids, if you have a fatty acid like this that just has a bunch of carbons, we call this saturated. Even though in very technical chemistry terms, the C double bond O would be unsaturated, but the tail is saturated. If we were to add a double bond here, we would have something unsaturated. Most naturally occurring fatty acids that are unsaturated have double bonds that have this type of an orientation. This is called a cis orientation because if we look at the two hydrogens connected here, or the two carbon chains, we notice that they're on the same side of the double bond. This is called a cis alkene or a cis double bond. And so this is a cis, got the end, cis unsaturated fatty acid. Normally, this is just called an unsaturated fatty acid because it's just commonly that they're all cis. Now, where that other term there, trans fats, comes in, is if you take a fat that has these types of fatty acids in it, these cis fatty acids, and you partially hydrogenate it, so you add a little bit of hydrogen, you can get these to isomerize, so you can get the stereoisomer or the diastereomer, where this now becomes a trans alkene instead of a cis alkene. So trans means opposite, so we'll have that same thing but opposite sides. So I want to make sure I'm drawing the same molecule here. So 1, 2, 3, 4, 5, 6. There's our double bond, and then 5 more. Okay. So same molecule, but now if we take a look at the substituents on that alkene, we see that they're on opposite sides of the bond there. And so this is called trans fatty acid rather than cis, a trans double bond there. And the reason this is important in that particular category is that for a long time, trans fats were used in processed foods because of their long shelf life. They were really resistant to rancidity, as well as just ease of use, as well as marketing, because you could say that there was no saturated fat in your food. But we now know that trans fats are actually much worse for you than saturated fats. And since they're not really necessary in diets or anything, they tend to not be there anymore. So the FDA has worked pretty hard to try to get those out of our diet, and we don't see them as much anymore. Occasionally, you can catch on an ingredient list, you can catch a partially hydrogenated something or other, but it's usually in pretty small amounts. All right. Will there be any use of the periodic table, like in regards to different valence shells? So, I mean, there is trans fat is a kind of unsaturated fat. Yes. So, I would answer that question a couple of ways. So, first, yes, you will have a periodic table on the exam, so you can refer to it. The way that we would talk about that. So in week 3, there's an objective of finding the number of valence and core electrons. So you should know the number of valence electrons. You'll also need that to construct Lewis structures, which is in the Lewis structure section, drawing Lewis structures of molecules. That, in order to draw those structures or to find those structures, you have to know the valence electrons. There's no drawing on the exam because it's through Blackboard, but there are questions that speak to those objectives. In terms of different valence shells, like, for example, like finding electron configurations, if you did that in your class, 1s2, 2s2, 2p6, that kind of thing, that's not in the objectives. Some sections, I think, do that. Others don't. That's not on the exam. So I would say yes, there will be some use of the periodic table with finding the valence shells. Again, the shortcut for that, you can always use the atomic number to find the total number of electrons and then count it from there. But then you have the column numbers. So 1 or 1a, 2 or 2a, and then jumping over to 3a, which is sometimes numbered as 13, 14 or 4a, and so on. And that can tell you the number of valence electrons. So if I throw up a periodic table here, you can see those different numbering schemes. The reason there's different numbering schemes, the A-B thing is an older way of doing it, which has some problems with the way that it categorizes things, especially when you get into the middle here. So people have wanted to move away from it because it's kind of less useful, but it still is nice for the valence electrons, like in this class or like in a general chemistry class, to be able to say, oh yeah, this works for the A's but not the B's. But the official actually correct numbering scheme is the numbers. So just 1, 2, 3, 4, 5 all the way across to 18. You can still use the second digit in those numbers to find the valence electrons. So for example, right above my head here is sulfur. That is in column 16. So it has 6 valence electrons. If we wanted to know the core electrons, we subtract from the total. So it's got 16 total electrons minus 6 valence electrons leaves 10 core electrons. All right, what else? Yes, you should know those conversions. The specific ones that you list are on the objective. So you should know that there are 760 torr in an atmosphere. Any other pressure-related conversions, you'd be given the numbers. Fahrenheit, Celsius, Kelvin, you should be able to interconvert those. Fahrenheit to Kelvin, the best way to do that is to convert Fahrenheit to Celsius and then just add 273 to get to Kelvin. Other stuff here. Does anybody have the exam open right now? Just copy in some questions. No, I'm just kidding. Don't do that. Yeah. 273 would be fine. We don't generally. Trying to think. Yeah, I don't think anything in the exam requires that kind of precision beyond 3 significant figures. Going through the objectives here. See if we find anything else that we haven't talked about yet. We've gotten a good amount of it. Oh, good. Yeah, molarity. Let's talk about molarity. Like, is it on there, or do you want me to go over it? Okay, great. Let's do it. If I can write the letter M. Okay. Molarity. So the most important thing to remember about molarity is the definition of the quantity. So molarity is always calculated as moles of solute divided by liters of solution. So moles per liter. Most of the other concentration, like mass percent, there's various different units you could use, like mass percent could be grams, could be pounds, could be kilograms, could be milligrams, whatever. Molarity is always moles per liter, moles of solute per liters of solution. So the key to calculating molarity is to convert whatever other quantities you have into moles and liters. So let's do an example. If we want to know the molarity of 20 grams of potassium chloride in 500 milliliters of solution. So 20 grams of potassium chloride in 500 milliliters of solution. If we want to know the molarity, we need, again, moles of solute and liters of solution. So the amounts that we have, and yes, this is on the exam, the amounts that we have here are grams and milliliters. So we can't use grams and milliliters here. We need moles and liters. So that means that we have to convert the grams to moles. We have to figure out how many moles that is. And we have to convert the milliliters to liters. We have to figure out how many liters that is. Then once we have moles and liters, then we can divide and get the molarity. So for the moles part, we're going to do a grams to moles conversions. So we look up on the periodic table our K and Cl. K is going to be, oh man, it's too small. I can't see it. It's 39 point something. We'll just say 39. We don't need to be that precise right now. So we'll go with 39 for K and 34.5 for Cl. So adding those up, no, sorry, that's not right. Not 34.5. Should be 35.5. This is why we need periodic tables, right? So we've got, oh, my head's in the way. Can anybody see that? 35.5, right? Yeah, okay. Thank you. So we'll call that 35.5, which is going to be 74.5 grams per mole. All right, so we've got 20 grams. Whoops. There it is. We've got 20 grams of KCl. And then we want to get rid of grams and instead have moles. So that's 74.5 grams in 1 mole. Do a little calculation here. So that's 0.27 moles of KCl. For our other conversion, I think we can do this in our head. 500 milliliters is half a liter, so that's going to be 0.50 liters. So I wasn't super organized here, but we have now our volume in liters, and we have our amount of solute in moles. So now we can divide those two. So the molarity, which we'll give with a capital M, is going to be 0.27 moles of KCl divided by 0.50 liters of solution. And then we would say that that concentration is 0.54 molar. So that's how you calculate a molarity. Again, make sure that your units are moles of solute and liters of solution, and you should be fine. And then you just divide those. The vast majority of mistakes in calculating molarity that I have seen have been because you're given the quantities in something like grams and milliliters, and then people want to just divide them just like that, and you can't. You need moles and you need liters to get molarity. All right, what else you got? Yes, you are allowed handheld calculators. I just changed the honor lock thing on Blackboard, so you should be fine with that. There isn't a whole lot of calculating on the exam. If you look at the objectives, again, the exam follows the objectives pretty closely, so most of them are descriptive, draw this, define this. The calculations, as we talked about, things like concentration and unit conversions primarily, moles. How many questions? It says on that Blackboard announcement, I think it's 60. Hold on, I got it up here. No, there's no essay type questions. It is, so there's that announcement on the test. On the Blackboard shell for the final exam that has all these details. It has 67 questions. There's no essay. There's a practice. There are two different practice exams on that shell. Neither one is really like a practice exam for the final. They're just kind of getting used to the format. So one of them is to kind of set up honor lock and make sure that's working for you. And then the other one is you can practice the different types of questions that are in the exam. So like there's multiple choice questions, there's numeric, like where you have to put in a number, there's some where you have to fill in the blank, like just fill in the blank with a word. There's some matching. There's no like essay sentence type stuff. They're all like, just quick questions. But yeah, I would say most of them are multiple choice, and then there's some enter the number and some like fill in the blank with words. It says it's in the instructions, but make sure that you include units if units are asked for. No, fill in the blanks are not case sensitive. It's kind of cool how Blackboard works if you're into that sort of thing. It actually, for the numeric questions, it separately asks if you want to require units, and so we do require units for this. But you only lose a tiny bit if you put the wrong units. And then for the things like the case sensitive, the fill in the blank things, they actually use regular expressions, regex, and that allows us to kind of carefully accept the correct answers and reject the wrong answers. Yeah, you're welcome. Sounds like everybody's good. So I don't know if anybody has anything else. We got about 5 minutes left. Other last minute topics or questions? All right. Well, again, if you have issues, Professor Lemkow and I are kind of taking shifts making sure that at least one of us is always on email, at least until like late at night. So if you need something, just send us an email, copy your instructor also if you're not in one of our sections, and we'll get back to you. We'll try to fix whatever's going on. If you need some more practice, some more review, if you're not in my section, all of our classes from my section from this year are still here on YouTube on this channel, so you can look them up and go through all that stuff if you want, or just go to the things that you need help with. Scored right away. So yes and no. I believe you'll see your like raw score of how much you got right when you finish the exam, but that won't be your actual final grade on the exam because it will be adjusted with statistics and stuff like that. So your instructor will get the adjusted scores after we do that, which can't happen until after everybody's done. So after the exam closes on Wednesday night, we'll start working on going through everything, checking everybody's stuff, working out the statistics, and then that next day, sometime Thursday, we should be able to get the adjusted scores to your instructor. Yeah, no problem. I'll send you the objective sheet. Yeah, you're welcome. Thanks for working so hard. Wish we could do it in person, but it's all right. Oh, thanks. Yeah, you like my bear? I like the sweater. Can I post this sheet? So, thanks. Are there any? Let's see. So I don't know of any practice tests for this exam. You can talk to your instructor if they have some practice questions. Certainly, thanks, Matt. The certainly your previous exams from the semester will be good practice. They should be on the same type of stuff. The final exam was a collaborative effort, so it's not just one person writing those questions. So yeah, I think whatever you've done this year will help prepare you. And I think that's a good idea. I'll just post the objectives to the final exam Blackboard shell, and that way anybody who needs to access it should be able to get it. I believe those should be also in they may be in your syllabus or something like that, but just in case you don't have them, I will post them also. All right. Well, if that's it, again, send me an email. Oh, here's another question. Great. Will the content be evenly distributed? More or less. I mean, with 67 questions, it's not going to be perfect because there's a lot of objectives, but yeah, more or less throughout the semester. It's not like weighted toward the end or anything like that. It's an overall exam. Yep. All right. Well, I'll watch for your emails if you've got anything else. But otherwise, have a great holiday, and I hope the final goes well for you. And we'll get the scores to you as soon as we can. So, good night, everybody. Bye. Thanks. Thanks, you too.